Welcome to the second video in the arrangement of electron series. We ended the last video talking about the photoelectric effect, and so we're going to pick up right there. We have a new scientist called Max Planck, and he has studied the emission of light by hot objects. We said at the end of the last video that when some metals get heated up, they glow, or they emit light. Well, he said that when they do that, the light that they give off is not in the form of a wave. He said that the light that they give off comes in these specific small amounts that he called a quanta. Okay, and a quanta is a packet of light particles, all right, which leads us to the word photon. Okay, a photon is a single particle of electromagnetic radiation having zero mass and carrying a quantum of energy. We'll define that in just a second. Basically, photon is a packet of light. All right, so if you want to identify that as a single, I guess you could actually say particle, that would be better. A single particle of light. So if light's not behaving like a wave, it's going to behave like a particle. Okay, so here's that word quantum. So quantum is the minimum quantity of energy that can be lost or gained by an atom. Okay, so a particle is going to have a certain amount of energy that an atom can lose or gain. All right? So Max Planck came up with this equation here, all right? And he said that the energy that atom can lose or gain is going to be equal to h, which is Planck's constant. He came up with this constant, he discovered it, okay? It's equal to this number right here, times f, the frequency of that radiation, the frequency of light that was being emitted. Okay, and remember, frequencies of light will determine what color that light is. We looked at that spectrum on those problems in the last video, and the different frequencies corresponded to different colors of light or to different types of radiation, X-ray and gamma and so on and so forth. And then, of course, we have c, which we told you in the last video is the speed of light, and it's equal to this value here. It's actually the speed of all electromagnetic radiation, whether it's light or radio waves or X-rays or whatever. And then a lot of times wavelengths on this scale are given in nanometers, and so 1 billion nanometers is equal to 1 meter. That's part of your metric system, and you're supposed to know that. It was times 10 to the 9th, okay, was equal to 1 meter. Back when we started the course, I had y'all memorize your metric system, so hopefully you still know that. If not, there it is. You're going to need to use that, okay? Here's that electromagnetic spectrum. I've kind of made it bigger here. We're using a picture that relates it to sizes of known things that we already understand, and it gives us those wavelengths here, okay? So when we do that times 10 to the negative 9th, so we're talking about nanometers here, we're on the size of molecules. If we look down here in our visible light spectrum, we've got 700 nanometers, 600, 500, 400, and it corresponds to some different colors here. So if we're on the 700 end, we're over here by red. If we're on the 400 end, we're over here by purple, or excuse me, violet, okay? And so as you get smaller, then we would move into ultraviolet, and even smaller X-ray, and even smaller gamma, okay? And the smaller the wavelength is, the higher the frequency is, and that means it's got more energy, okay? And because of that, Because of that increase in energy, that means these things are more harmful to you. That's why you can get skin cancer and things from ultraviolet light, because it's got more energy than regular visible light. And that's why when you go to the dentist and they take your x-rays, they put a lead vest over the top of you, because x-rays can mutate your DNA inside your cells because it's got more energy. And that extra energy can be harmful to you. And then gamma rays, those can kill you, all right? Too much of this stuff can kill you by way of cancer, but gamma rays, that can kill you, almost immediately if you have a large exposure to it. These are the kinds of radiation you would get working around nuclear power plants and things like that. So those guys have to be super crazy careful working around that kind of stuff. All right. So let's do a practice question. We have a ruby laser produces red light that has a wavelength of 500 nanometers. Calculate its energy in joules. Before we start, I want to quickly draw your attention to something so that you don't get confused. This chart here is going from larger wavelengths to smaller wavelengths, okay? And the chart over here is going from smaller wavelengths to larger wavelengths, okay? So that's why they're flipped. The violet is on the left-hand side in this picture, and it was on the right-hand side in the other. And it's just because they're choosing to look at it going from smaller to larger in this picture. Okay, so this ruby laser is producing red light. Okay, the fact that we're talking about light means it's going to move at the speed of light, so we'll have to use that number. And they're asking me about energy, so I know I'm going to have to use Planck's equation. So let's write that one down. We have energy is equal to Planck's constant times the frequency. Okay, and then this one is what I call a combo problem, because they also gave me wavelength. Now you'll notice wavelength is not part of this formula, but it was part of our speed of a wave formula. So I'm going to write that one down because it had that in there. Okay, now hopefully you'll notice that these two formulas here share something in common with each other. They share frequency in common with each other. So if we can calculate the frequency using this equation, then we can plug it in right here and figure out the energy with this top equation. Okay? So we can go about solving this problem one of two ways. The way I just described it to you, where we solve this for frequency and then we plug it in here, or we can solve this equation for frequency and then plug the new equation in up here and do everything all at once. I'm actually going to go through both with you so that you can figure out what you like best. Okay? So remember, we're going to circle the thing that we want, which is frequency. And the reason that we are choosing frequency, by the way, again, is because that's the thing that both of these share in common with each other. So we're going to leave it alone, and then we're going to undo what's happening to it. And right now it's being multiplied by the wavelength, so we're going to divide both sides by the wavelength. Okay? So we know that frequency is equal to the speed of the wave over the wavelength. And then we plug in. We know that this is light, so we're going to use the speed of light here. And we've got wavelength, which they said is 500 nanometers. Okay, we can't use nanometers down here because we have meters in our unit up here, and those won't cancel each other out. So we actually need to use some dimensional analysis real quick. We need to say 500 nanometers over 1. And then remember, right over here, you were told that 1 billion nanometers equals 1 meter. So I'm going to kind of shorten that because 1 billion is the same thing as saying 1 times 10 to the 9th nanometers is equal to 1 meter. So we'll plug that in our calculator and see what that is. And that's going to be 5 times 10 to the negative 7th meters. Okay, so that's what we'll put down here on the bottom. 5 times 10 to the negative 7th meters. Now the meters will cancel with meters, and we'll be left with 1 over seconds, or the seconds you'll notice here is in the denominator, so that's hertz, which is the correct unit for frequency. And we're going to get 6 times 10 to the 14th hertz. Okay, that is really fast. That's a huge frequency. Okay. Now we're going to take that frequency we just calculated and plug it in up here so that we can get the energy. And since we're being asked for energy, this is already set up to solve for energy, so we're doing good. So we've got energy is equal to Planck's constant, which is 6.6. Oh, that's a bad 6 there. Let me fix that. 6.626 times 10 to the negative 34 joules times seconds times 6 times 10 to the 14th hertz. Okay, that's what we calculated just a second ago. Alright, so now we'll plug that into our calculator and see what we get. Alright, I'm getting 3.9756 times 10 to the negative 19th joules. Now, where am I getting that joules from? Remember, hertz is the same thing as 1 over seconds, meaning that seconds is in the denominator. Up here, you'll notice that seconds is in the numerator. So, those cancel out with each other and they leave you with joules. Okay. Now we need, of course, to do our significant digits. We were given in the problem one significant digit, so we can only have one significant digit down here. So the 9 rounds the 3 up, so we've got 4 times 10 to the negative 19th joules of energy. Okay? Alright, I said I was going to do this 2 different ways. I just did it this way where we solve for frequency in the wave equation and then we plug it back into Planck's equation. Now we're going to do it where we just do everything in one step. Okay, so we're going to again solve this for frequency by dividing by wavelength on both sides. So that means that frequency is equal to the velocity divided by the wavelength. I can plug this stuff in right here. So I'm going to say energy is equal to Planck's constant times, and now instead of saying frequency, I'm going to plug in V over wavelength. Okay, now I can just solve everything all at once, putting all of the numbers in at the same time. Okay, so we'll have energy equals Planck's constant times the speed of light divided by the wavelength. Okay, so you could plug all of this stuff in your calculator. You're going to want to type this in first and get an answer and then multiply it by that. And when you get done, you should end up with E equals 3.9756 times 10 to the negative 19th joules. And then we do our sig fig stuff again. We can only have one sig fig. So we finally end up with 4 times 10 to the negative 19th joules. Okay, so either way you choose to do it, you should get the same exact answer. Okay, a minute ago when we were talking about photoelectric effect, I used the terms excited state and ground state. And so let's talk about what that is exactly. Ground state is what we call the lowest energy state of an electron, and that's where an electron likes to be. It's an area or a state of low potential energy. Okay, so imagine you standing on the ledge of a cliff or you standing firmly down on the ground. Which would you rather do? Would you rather be balancing precariously at the tip of the ledge, or would you rather be standing safely on the ground? That's kind of my example for ground state and excited state. Excited state would be up on the ledge, and ground state would be safe on the ground. So obviously an electron likes to be in this low energy state rather than in this high energy state. Okay? So what happens is you've got some electrons that are zipping around their energy levels here. Okay? And then a photon of light comes in and hits an electron that was zipping around the nucleus. That gives that electron some energy, and that makes it jump up to an excited state. Okay, and it's going to stay in this excited state until it loses that energy. And so maybe it jumped up to this energy level, so it corresponds with this picture. That's just what I'm saying. So it's zipping around this energy level, and then it needs to give off that extra energy. So it emits a photon of light that you would actually see this atom, whatever it is, you would see it glow because some light was shot off of it. When that happens, the electron loses that extra energy and goes back down to ground state. So here it gets energy and jumps to excited state. So maybe it jumped to this one, maybe it jumped to that one, maybe it jumped to a higher one that's not even pictured yet. And then when it gives off that energy in the form of light, then it drops back down to ground state. Okay, so what we're looking at right now is called the continuous spectrum. That's this right here. It's all of the colors in white light or visible light. Okay, so it's a continuous range of all the frequencies in the visible spectrum of electromagnetic radiation. Okay, so we go from the red to the violets. Alright, well, different elements will give off different line spectra, is what it's called. So when we just talked about an electron moving to the excited state and then falling back to ground state, well, remember, when they fall back down to ground state, they emit light. Okay, and if you split that light using a prism, just like we could split white light and get all of these colors in the spectrum, if we hold a prism up to an element that is giving off light because the electrons are falling back down into ground state, we can split the light that it's giving off, and we'll see these different lines of color appear, and then there will be these dark sections in between. Okay, so this is the line spectrum for hydrogen. All right, and scientists actually can use these line spectra to figure out what distant planets are made of and what stars are made of. We can put a telescope, we can look out into space with a telescope at planets and put a prism in front of that telescope, and the light that comes from stars and other planets will be split, and then we will see these line spectra. And if the line spectra matches, let's say for example this line spectra right here, then we know that that planet has hydrogen in it because the hydrogen line spectrum is being produced. And so every element gives off its own distinct line spectrum like a fingerprint, and so we can determine what other planets and stars are made of by it. Now, one scientist looked at this hydrogen line spectrum and he saw something that nobody else had seen yet. Okay? He recognized that every time that a line is produced, that must be where an electron had fallen from excited state to ground state. And so he said that they always occur with these distances between them. Okay? And so he said that must be the energy level. So here must be the first energy level, and here must be the second, and here is the third, and so on and so forth. So this is where we got the idea of energy levels for electrons, and that they would orbit around the nucleus in these distinct areas, these levels away from the nucleus. If you said right here's the nucleus, then there would be the first energy level. There's the second, there's the third. Well, I bet you can guess the name of the guy that came up with that. His name was Niels Bohr, and that's where we got the Bohr model of the atom. I want to show you a little video clip that goes into some more detail about this ground state and excited state and atoms giving off light. So we will continue in the next video with Niels Bohr and the Bohr model of the atom. As always, thank you for learning with me today, and I'll see you next time.